Hello, good morning. This is Naz from NB Network Lessons. Hope everyone's doing well. Today, date is August 12th, 2024, and this is physics lesson 20, and we're going to discuss instantaneous acceleration in terms of physics. But before I do that, the quote of the day. The quote of the day is learn from past, stay in present, and plan for future. Let me say it again. Learn from past, stay in present, and plan for future. Thank you. And having said that, let me go ahead and dive into instantaneous acceleration. Everybody knows, like I explained you earlier, in my lecture, what is a instantaneous velocity. Instantaneous velocity is you're driving from point A to point B, and I want you to determine velocity at this particular instance. Okay. So that is instantaneous velocity. Similarly, when you're driving on the road, you give gas gradually, and then your speed is increasing, right? Your speed is increasing, you're accelerating. So I want you to find acceleration at a certain instance. And that's exactly what instantaneous acceleration is. So let me go ahead and recap a little bit, and then we'll dive in. Let's look at this graph right here. This is a position graph, okay? Or you can say a distance graph. So I have on x-axis, I have time in seconds, and on y-axis, I have distance in meters, okay? And then the function is you have a graph, sort of like a parabola shape, going like this. All right, going like this. So now what we want you to do is, this is kind of like a recap, okay? I want you to find velocity at this point right here, and let's call this point A. All right, so how would you do that? I have not given you any numbers, but theoretically, how would you find instantaneous velocity at this point A? Well, if you recall, what we do is that in order to find instantaneous velocity at this point A, we pick another point. Let's say we pick point B right here, right? And then what we do is that we join these two dots right here. My line might not be straight, but forgive me for that. Now, what we have to do is we say, okay, right here, right here, this is my delta t, okay? This is initial time, this is final time, and this is the difference of those, tf minus ti. Now I extend the graph and go towards distance. Okay, so this right here is my delta x. Okay, so now if I ask you, hey, can you tell me, let's say you have a point A and point B, and you're driving between point A and point B. All right, if I ask you what is your velocity over here, what you would do is that, let's say the distance is 10 meters and time it take you to drive from point A to point B is 2 seconds, you will just straight away say, yeah, velocity is 10 over 2, which is equal to 5 meter per second. All right, this is the average velocity. But in this particular case, I want you to find the instantaneous velocity at point A. All right, so now for that, what we do is that, that's easy. What we can do is we can say instantaneous velocity would be equal to delta t over, sorry, delta x over delta t. This is my delta x right here, and this is delta t. Essentially, when you find velocity, what you're doing is that basically you're finding the slope of the line. Rise over run, okay? Rise over run. So that's exactly what it is that. So the derivative of distance is velocity. Okay. So this is instantaneous velocity dx over dt. We're not done yet. The true instantaneous velocity would be if this delta t becomes smaller, 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 close to zero. Okay. So then what we do is that we put in a limit. Okay. We say instantaneous velocity would be equal to limit delta t approaching zero, delta x over delta t. So that is the true instantaneous velocity right here. Makes sense? So if you have this point A and B, okay, you can still get the instantaneous velocity, but the results might not be accurate. The results would be accurate the closer you get to the point A. And how do you get closer to the point A? By shrinking the time. Shrink the time, get as much closer to zero as possible. Not zero, but as much as you can get closer to zero. Now, same concept applies to uh, acceleration. So let's go ahead and do that. I'm going to go ahead and draw another graph. All right. Let's say initially we drew a position curve. Now we are going to draw a velocity curve. Okay. This is time in seconds. And this right here is velocity in meters per second. Okay. I'm going to essentially sort of like draw the same graph which I had before, kind of like a parabola shape. All right. Now I want you to find instantaneous acceleration, not velocity, at this point A. How would you do that? Same concept. You pick another point right here. Let's say point B. Okay. You join these points right here. And this right here will be your delta t, and then move towards the velocity right here. This right here would be delta v. Okay. So now if I ask you to find acceleration, instantaneous acceleration at point A, how would you do it? Well, pretty much same constant. So instantaneous acceleration, I can call this instantaneous acceleration would be equal to delta v. First of all, I would say limit delta t approaching zero, delta v over delta t. Okay. So that is going to be my instantaneous acceleration at point A. I mean, I could calculate by using, delta v and difference delta t between point A and B, but it would not be accurate. The smaller the delta t is, the better the answer is. Okay. So what have we learned from here for my calculus lovers? Derivative of position is velocity. Derivative of velocity is acceleration. All we're doing is finding a slope. When you find a slope of a line, you get velocity. When you find a slope of a curve or a line or velocity, you get acceleration. Thank you so much for watching. I really appreciate it. Share the knowledge as much as you can. And if you like the contents, please go ahead and give me a like. Thank you and take care of yourself. Bye.